Hello everyone, I'm Luiz Soares from the Federal University of Minas Gerais in Brazil. I'm currently pursuing a master's degree under the supervision of Fernando Pereira, and we started this project in the beginning of the last year. And basically, what we want is to come up with a way to transform cryptographic programs so that the new version is guaranteed to be free of side channels. So, before we talk about the transformation itself, let us see what are side channels and why they are problematic. Side channels are basically vulnerabilities that can be explored by an adversary to obtain sensitive information from a program. And there are a lot of types of side channels. For instance, those ones based on the running time of the program, on the layout of the cache, or even on power consumption. And year after year, we heard news about side channels being discovered. So, for instance, in 2018, many flaws were discovered that affect multiple CPUs like Intel and AMD. Flaws called meltdown and spectre type. And in 2019, this new side channel called zombie load, also affecting Intel CPUs, was discovered and fixed. And last year, again, new sidechannel attacks were described for Intel CPUs. In this project, we are interested in the first type, sidechannels that leak information through the differences on the execution time of a program. For instance, consider this function called OFDF. You may have noted this weird name, OFDF. And here O means operation invariant and D means data invariant. The F stands for false, so in this case, this function is neither operation nor data invariant. This will make sense in a minute. The number of iterations performed on each call to OFDF depends on whether the elements of the arrays are the same or not. Consider the two extreme cases. The first is when none of the elements are equal. In this case, the loop will be executed only once. On the other hand, if the arrays are the same, the loop will be fully executed. Hence, depending on the inputs, the number of instructions, and consequently, the execution time, will be different. And this can be explored by an adversary, so this person can collect information based on the difference between the execution time of this program. And this way, the goal of this project is to eliminate this kind of side channels, timing-based side channels. And we call this transformation Isochronification. So for that, we will define transformation T. And this transformation will take a program P and return a new version P prime without the side channel identified on the original code. The result of the two functions must be the same for any input, so P and P prime will be semantically equivalent. Furthermore, P prime will always be operation invariant and data invariant whenever possible. And also, the transformation will be memory safe. And by memory safe, we mean that it will not introduce any possible bug that could not occur in the original version. So before moving to the transformation, let us see a few properties. First one is data invariance. A program is data invariant if it always accesses the same memory address regardless of any input, the same memory address in the same order, regardless of any input. Note that OFDF, as I said before, is not data invariant due to the return statement inside the loop. Here is a modified version that fixes this problem. OFDT is data invariant because it will always access A0, B0, A1, B1, and so on, no matter what the values of A and B are. Similarly, operation invariance means that this function will always perform the same operations regardless of any input. Here, OFDF-U is basically OFDF, but with two iterations of the loop unrolled, just for simplicity. Note, for instance, that the second comparison will only be executed if the first one fails. This is not what we want. We want the function to perform the same operations always. So what can we do? Well, we just need to eliminate the conditional statements. And in this case, this is quite simple. Here is a version of this function that is operation invariant now, OTDT. But now we have a problem. And recall that I said that the transformation should not introduce any bugs. It should be memory safe. Well, what happens if there is a call to those functions with arrays of size 1? In the first case, the second access would not be executed due to the first return statement. But for the transformed function, the second access would still be performed, but A1 and B1 are not valid memory cells. Thus, we introduced an out-of-bounds access that will not occur at all in the original version. This is basically what was proposed by Wu et al. In the paper called Eliminating Time Side Channels Leaks Using Program Repair. And what we want here is to improve their work by not introducing any kind of bugs. Unfortunately, not every program can be safely transformed. Consider, for instance, OTDF. This version is operation invariant, but is not data invariant. It's quite similar to the previous function, OFDF. Actually, OFDT. But it takes one additional parameter t, which is used in the comparisons. Note that now, there is no way for us to tell which positions will be accessed, since we don't know the values in arrays A and B. Thus, we will not consider this kind of functions. There is no hope for them. Nevertheless, there must be a class of programs that can be safely transformed, right? To identify them, we have to find the concept of data consistency. Data consistency is basically a weaker version of data invariance. It also requires all memory access to be the same regardless of any input, but without imposing constraints on the accesses ordering. To illustrate, consider this bar function. It will always access the first n positions of array A, regardless of whether it takes the true or the false branch. If we can remove the condition statement without changing the result of the function, then we are done. Every data consistent program can be fully isochronified without introducing possible bugs. And this is exactly what we want. This is the best case. Another example. OFDT is also data consistent, since it is data invariant. But what about OFDF, our original function? It is not data consistent, but also does not use a third array in the comparisons, like OTDF. So, can we transform it? The answer is sort of. We could fully isocronify it if we know that all memory access are safe, but that's not always possible. Thus, for this kind of programs, we need to make compromises. A memory contract is a triple, formed by the function f, the array A, and an integer n. This triple is a precondition stating that whenever f is invoked, the array A contains at least n valid cells. Here's a version. Here's an image that illustrates this concept. We have an array with m positions, and we know that the first n positions are always safe to be accessed. So we can use this in our transformation. And here's a version of OFDF that incorporates two memory contracts, one for array A and another for array B. The first comparison is always performed, the first comparison in the loop, so we keep it. The original loop was split into two. In the first one, we know that all positions are valid. All positions that are within the bounds imposed by NA and NB. Thus, we can safely transform this piece of the function. Note that if both NA and NB are greater than the max number of iterations, then the function will access all the positions, regardless of the values inside the arrays A and B. This is the compromise we make. After transforming this function, the repaired code will be that invariant whenever possible, but not necessarily always. If there is still elements to be compared, we move back to the original behavior, check if the previous compared elements were the same. If not, return immediately because the next comparison is not safe anymore. What the transformation presented in the paper does is basically eliminate conditional statements while keeping the semantics of the original code. I'll be using this very simple function foo to illustrate a transformation step by step. Question: is this function data consistent? The answer is no, it is not. Note that the array A will only be accessed if C is true. Hence, we need to modify the signature of the function to incorporate the memory contract. And now we know that whenever the value of I is within the bounds imposed by NA, we can safely access the array A at index I. But wait, when C is false, the function should return -1, but now it will return A at position I, when I is less than NA. That's not right. To fix this problem, let's first unify the return points. That will simplify things a lot. We can do that by creating variables that shall store what will be returned. But note that despite our efforts, this function is neither operation nor data invariant yet. We need to eliminate this conditional statement. But if we simply delete it, the function will access array A even when it should not. Let's see what we need to do. And we need that the memory access inside the if statement to happen always. But we cannot eliminate the if at all. What if we create a new memory access? We'll use what we called as a shadow memory, or SH, which basically will be a memory address holding some dummy value. Now, regardless of the branch we take in the conditional statement, there will be a memory access. Seems like we are in the correct path. Now we can safely eliminate the conditional statement. That's the base of the idea behind the transformation, eliminate all of them. For that, we use constant time selectors, which in this example are the ternary operators. Let's take a final look into this function. We have the memory contract discussed before. We use a shadow memory for access that should not occur in the original code and are not safe within the bounds imposed by the memory contract. And we use constant time selectors to eliminate the difference in execution time due to conditional statements. And there it is. We have a function that is also operation invariant, is memory safe in the sense that bugs that would not occur in the original version will still not occur in the new version, and is data invariant whenever I is within the constraint imposed by the memory contract. We have implemented this transformation, or program repair, in LLVM, and using this prototype, we have conducted experiments which the goal was to answer 3 research questions. The first one is the time taken. What is the time taken to run our pass? The second is what is the time overhead that our program program repair technique adds onto programs. And similarly, the third one is about the size overhead that our method adds to programs. We needed something to compare against with, so we have used the artifact from Wu et al.'s paper, which is that one that introduced possible out-of-bound access to programs that I talked about earlier. And we have used a subset of the benchmarks delivered with Wu et al.'s artifact plus some of the benchmarks distributed in CTbench. Unfortunately, SC Eliminator, which is how Wu et al. Called their prototype, could not be applied onto a few benchmarks, either because it produced the wrong code or it crashed. Such cases are represented in the charts without visible bars. You can find all of the benchmarks available in Citibench in this GitHub repository. And we have also used OFDF, that function that I introduced in the beginning of the presentation, to conduct an empirical restudy, considering arrays of different sizes. Let's start with the first research question about the repairing time. SC Eliminator did not work for the first 3 benchmarks. In general, we can see that our tool took much less time than SC Eliminator. Implementation details may be one of the reasons for that. Furthermore, Wethal's method required some preprocessing in order to transform conditional statements into single-entry, single-exit regions, which is not necessary in our implementation. When analyzing our FDF function, we can see that our implementation behaves much better as the size of the input grows. And now let's move to the time overhead imposed onto programs. Here we have the results for the unoptimized code, and we can see that in both, in this case, our tool won most of the time. And the same is true for the optimized versions. We have optimized code with the flag 01 of LLVM. So in the optimized versions, we also won most of the times. And here is the result for the OFDF function. First, the unoptimized case. But in this case, we have not compared our tool with SC Eliminator because Wethal's tool generated incorrect code, probably due to implementation bugs. So what we can see in this plot is that the execution time of the original code grows when the inputs are the same but remains the same when the first element already differs. And that's the difference in execution time according to the input. That's what can be explored by a person who wants to collect sensitive information. And this is basically, as I said, this is basically what a time-based sidechain is. And down here we have the same comparison, but this time we have optimized the programs with Clang 02. And note that the running time of the transformed version behaves the same for both inputs. I mean, regardless of the inputs, even in the first case or the second, the behavior of the plot is the same. And finally, let's take a look at the size overhead that we add onto programs. Again, we can see that our tool beats SC Eliminator in most of the cases in the unoptimized version, and this remains true for the optimized version. So finally, let's see what happens in the case of OFDF. The chart in this case is in logarithmic scale. We can see that we do add lots of instructions, and this is somewhat expected, but there are places for optimizations. Because when comparing the original and repaired code after optimization applied by the O1 pipeline, the difference drops considerably. So that's basically the idea behind the technique described in the paper. So let's summarize what we have here. First, we have a method to eliminate conditional statements that preserves the semantics of the original code and do not introduce any bug that will not occur in the original version. It runs faster than Wethal's pass. In general, it adds less time overhead onto programs than the comparative work, and also adds less instructions onto programs. As a downside, the technique as described in the paper requires functions to be loop-free, and fortunately, the idea can be easily extended to handle loops with constant bounds. As for loops controlled by variables, if this variable does not carry sensitive data, then that's fine. Otherwise, we don't have a perfect solution yet, and it may be the case that solution does not exist, but we are working on it. In order to compute the lower bound used in the memory contracts, we try to infer the size of the arrays or structs. passed to functions. However, this is not always possible and it is not an easy task. Therefore, for data inconsistent programs, sometimes there might be cases where data invariance will not be guaranteed at all. And that's it. Here are some links. We have an artifact, which is available in Zenodo, and also in Docker Hub. There is a Docker image containing the benchmarks and the binaries that are necessary. And we also have an online version of the tool. And we have the code is publicly available on GitHub, so you can check if you want. And that's it. Thank you all.